So here I am, I'm asking the central question, just what is a buffer and how does it do its job, and what sort of calculations and how would we make a buffer, that kind of stuff. So I'm going to start off with this screen right here. So I'm looking at page 183, and I have my 3 beakers set up with different solutions. And these are solutions of acetic acid, 0.1 molar acetic acid, 0.1 molar sodium acetate, which is the conjugate base of acetic acid, and then 0.1 molar of both the conjugate acid and the conjugate base. And I give a variety of pHs there. So I'd like to highlight that in that first beaker, what we have is just a weak acid. And if you were asked to do a calculation to actually determine its pH, you could. We saw earlier that we can take a shortcut. We could determine the hydronium ion concentration by using the Ka times the original acid concentration all to the square root. That was the topic of last Friday's class. You need to do a check. You need to calculate the percent ionization to make sure that the check is valid. But we could do this calculation, and we would indeed find that the pH is equal to 2.87 for a 0.1 molar solution. We could also work with this sodium acetate. And just to be clear, this is CH3COO negative. You've got the conjugate base. And then, of course, we've got the negligible acid, the sodium ion. Okay, so that's what's going on there. And we could determine also the pH by finding, first of all, the hydroxide concentration, then the pOH by using Kb times, and I'm going to represent that conjugate base as A negative, all to the square root. So those are situations where you have predominantly either weak acid or predominantly weak base present. But one of the calculations that we did also last Friday was what happens when you have a large amount of each of the conjugate acid and conjugate base. And when we've been talking about titrations, we've been talking about equal amounts. But they don't have to be necessarily equal amounts. You just need to have substantial amounts of both. We saw that actually there's a third kind of calculation we can do, which is based on the Henderson-Hasselbach equation. pH is equal to pKa plus the log of the conjugate base concentration divided by the conjugate acid concentration. And in some ways, this is the easiest type of calculation, but you can only do it when you have reasonable amounts. And today, we're going to kind of unpack what we mean by reasonable amounts of the conjugate acid, conjugate base. In our case here, we've got equal amounts of conjugate acid, conjugate base. Therefore, of course, that's log of 1. Log of 1 is equal to 0, and the pH would equal to pKa. Now, what does all of this have to do with a buffer? Well, looking in your course pack, on page 183, I have 2 definitions of a buffer. So one of the definitions reads an aqueous solution that minimizes the change in pH upon the addition of strong acid, strong base. So that's a functional definition. That says, what does this thing do under certain circumstances? But I think what's going to be equally important is for us to have a compositional definition. The compositional definition is saying, well, what does a buffer contain? So here we have an aqueous solution that contains weak conjugate acid-base pair in a 1:10 ratio. So let's unpack that a little bit. But if we now sort of jump down to the key question number 1, which of the above solutions are an example of a buffer or a buffer system? And I hope you will agree with me that only one of these beakers has a buffer system. And rather than get you to type in the chat or circle it or whatever, I hope it's pretty obvious to you that the one that has a buffer system, the one where the conjugate acid, conjugate base system is within a 10-to-1 ratio, well, it's got to be this guy, right? So yes, we've got conjugate acids, conjugate base, but if you want to have, you need to have both present in a reasonable amount. What's a reasonable amount? Within a 1 to 10 ratio. So yes, this C here does represent our buffer system. But I don't want you to be thinking that a buffer system always has to have equal amounts of the conjugate acid, conjugate base. That's sort of an ideal situation where you've got, quite a large amount or substantial amounts of both. But minimally, it has to be that they're within a 1 to 10 ratio. Key question number 2 then goes on to ask, well, confirm that the pH in C is actually correct. Well, let's go on to do that. So key question number 2, we see that we've got the acetic acid concentration of 0.1 molar. We see that we've got the acetate, that is its conjugate base concentration at 0.1 molar. And here we're allowed to use the Henderson-Hasselbach equation. So there it is. Remember that you've got this in your formula sheet. And sometimes these things are written as base over acid. Be careful. This is not strong base that you might use in a titration. This is the conjugate base of that corresponding acid. So be careful how you use the Henderson-Hasselbach equation. But of course, if we now plug in the values, right, I've already mentioned these are conjugate acid, conjugate bases. We're going to ignore the sodium ions. If we plug in these values, then we'll get something like this. And part of what we're doing here is, in order to plug in values, I need to take the Ka for my acetic acid, which is 1.8 times 10 to the negative 5. Now that value will either be given to you or you'll be looking it up in a chart. Now, in part also because of I was already given what that pH was and that we've got equal amounts, well, then I also knew that that would be equivalent to the pKa. So just to be clear, this Ka, pardon me back, I'll go back here. This Ka would be given or in a chart that you would have access to. So of course you don't need to memorize or know Kas. These would be given. So then if we take the negative log of 1.8 times 10 to the negative 5, we of course will end up with this 4.74. Plug that into the Henderson-Hasselbach equation. Well, pH is equal to 4.74. So we've just confirmed that indeed that pH is correct. Now there's a reason why I wanted us to start there, because I want you to see, in a sense, the buffer range. So I'm moving on here, and I'm kind of using these key questions to guide us a little bit in what we're presenting. So the key question number 3 then says, calculate the pH of a buffer that contains, and note we're changing things a little bit, 0.1 molar acetic acid and 0.01 molar sodium acetate or acetate. So you can see that we've reduced the amount of acetate solution. Now, this is not a difficult calculation, so let's just go ahead and do that. All right, so here are the conditions. We're leaving the acetic acid as 0.1 molar, and we're changing the acetates to 0.01 molar. It's the same Ka, therefore the same pKa. So perhaps you're getting a sense that with these buffer systems, the pKa is a pretty important determinant, or the Ka is an important determinant, and then we take the negative log of that. So that ultimately was going to determine what the pH is, and then it'll just be this ratio of the conjugate acid and conjugate base that will sort of tweak the pH to a new value. Now, maybe some of you have gone ahead and done the calculation, but in some ways, I'd like you to be thinking about it in a conceptual way. So if I now sort of plug in the values, and obviously, once again, we get this 4.74, but if my A negative is 0.01 and my HA is 0.1, well, of course, when I do this math, I end up with log of 0.1. So as I say, I know you can just plug in the values, but when you calculate log of 0.1, I think you will see that it equals -1. It'll be a negative number. Anytime you take the log of a fraction or a log of a number less than 1, you're going to get a negative value. So here's the pH, 3.74. Does that make sense? Would we expect a pH that's more acidic than 4.74? And if you, again, look at the buffer composition, which component do we have more of? Well, hopefully it's clear to you that we have more of the conjugate acid present. So it should make sense that the pH will be lower. The pH will be more acidic. So as I say, the most important determinant for a buffer for the pH is this pKa. And then it's going to be either a little bit lower than the pKa or a little bit higher. Lower means that you've got more of the conjugate acid present. Higher would mean you have more of the conjugate base. Again, you can just plug in the numbers, but I hope you see that relationship. So we just did the key question number 3 together. I'd like to ask you to go ahead and do the key question number 1. Oh, darn, I didn't mean to say that. The key question number 4, where you change the parameters yet again, or change the concentrations yet again. So I'd like to pause for you to go ahead and do the next calculation and kind of reflect, does that make sense? Is that what you'd expect? So the key question number 4, we're changing the concentrations. In fact, I think I'll put this out here in front of us. Okay. Actually, I think I just want to make that point again, and maybe you might want to write this down now that I've got it on the screen here, that this pH for the key question number 3, the fact that that pH is a more acidic pH, this makes sense because the HA, the conjugate acids concentration, is greater than the conjugate bases concentration. Once again, we expect that the pH essentially is going to be determined by the pKa. So, of course, we can plug in the values. Now, as we see, the conjugate bases concentration is larger than the conjugate acids concentration. So the conjugate base here is at around 0.1 molar. The conjugate acid is around 0.01 molar. When you take that ratio, we see a value of 10. Of course, the log of 10 is equal to 1. 4.74 plus 1 is 5.74. Does this make sense? Well, it's a pH greater than 4.74. And we'll add this next comment then. This makes sense because the A negative, the conjugate bases concentration, is greater than the conjugate acids concentration. That, in a sense, the anchor point is when the two concentrations are the same, because then the pH equals the pKa. And then you branch off a little bit on one side and then to the other side. Now you'll see that I intentionally chose situations where either the conjugate base was 10 times larger than the conjugate acid, or the conjugate acid was 10 times larger than the conjugate base. I hope you see that this gives us then a range of, on the high level, 5.74, down to the low level, 3.74. So I'm now looking at the key question number 5. What is the pH range? Well, through this calculation, we're starting to see that this is the pH range. pH equals the pKa at 4.74. If you have 10 times excess of HA, so if HA's concentration is greater than the A negative concentration, and we specifically chose 10 to 1, or alternatively, on the other side, the conjugate bases concentration is 10 times larger than the conjugate acid's concentration, then we see a pH of 5.74. The buffer that we're interested in terms of composition, is when the conjugate acid and conjugate base are within a 10-to-1 ratio. So any pH from around 3.74 up to 5.74 is within the buffer zone of this buffer system. So if you look a little bit further down, you'll see that I then write, in general, we'd say that the buffer range or buffer zone can be described. And so here's a way that we actually show it. It'd be like this, and it's simply plus or minus 1. So whatever the pKa is of our conjugate acid, plus or minus 1, that's the buffer zone.